The year is 2247. Earth is a memory. A ship carrying the last hope of human exploration has been sailing through nothing, absolute, total nothing, for over 2 centuries. The crew were born on this ship, their grandparents were born on this ship, and right now, the captain is standing at the observation window, staring into a void so deep and so silent that it has driven 3 people insane this year alone. They are not even halfway there. And here's the part that will change the way you look at the night sky forever. I'm going to tell you exactly why at the very end of this video. But first, quick question before we go any further. Where in the world are you watching this right now? Drop it in the comments, seriously, because what you're about to learn makes geography feel wonderfully, almost painfully small. All right, let's rewind. Not to 2247, further back, to right now, tonight, to the moment you step outside, look up and see a tiny, quiet dot of light that has existed for 4.85 billion years, completely indifferent to whether we ever reach it. That dot is Proxima Centauri, our nearest stellar neighbor, and we will never reach it. Not probably won't, not unlikely to, never. Here's why that's not pessimism, it's physics. Let's start with a number most people hear and immediately stop processing: 4.24 light years. That's the distance to Proxima Centauri, 4.24 light years. Sounds almost casual, right? Like something you'd see on a highway sign. Proxima Centauri, 4.24 light years. Next exit. Here's what that actually means. Light travels at 300,000 kilometers per second. In 1 second, light could circle the entire Earth 7.5 times. In 8 minutes, it crosses the entire distance from the sun to you. That's fast. That is the fastest anything in the universe is permitted to travel. Not can travel, permitted. The universe has a hard speed limit, and light is already at it. And at that speed, the absolute maximum velocity the laws of physics will allow, it still takes 4 years and 3 months just to reach the nearest star. Now think about how fast we actually go. The fastest spacecraft humanity has ever launched is the Parker Solar Probe. At its closest approach to the sun, it hits roughly 690,000 kilometers per hour. That sounds enormous. That would get you from Cairo to New York in about 20 seconds. At that speed, reaching Proxima Centauri would take over 6,000 years. Let me give you a way to feel that number properly. 6,000 years ago, writing had just been invented. The wheel was new. The pyramids hadn't been built yet. If the ancient Egyptians had launched a spacecraft the moment they started laying the first foundation stones of Giza, it would still have 1,500 years left to travel. And the Parker Solar Probe only reaches that speed because it's falling toward the sun, borrowing gravity like a slingshot. A ship heading outward, away from the solar system toward another star, would be fighting gravity the entire way. It would be slower, much, much slower. Our best real example of that is Voyager 1, launched in 1977, officially left the solar system, moving at about 61,000 kilometers per hour. It is the furthest human-made object in existence. At Voyager's speed, reaching Proxima Centauri would take 73,000 years. Human civilization, from the first cave paintings to smartphones, spans roughly 50,000 years. We would need longer than the entire span of recorded and prehistoric human history just to reach the star next door. So the obvious answers sound simple. Go faster, build a bigger engine, burn more fuel. And that's exactly where the universe stops you cold. There's an equation in aerospace engineering called the Tsiolkovsky rocket equation. It was derived in 1903, and over 120 years later, it is still the wall that every rocket scientist on Earth runs straight into. Here's what it says in plain language. To go faster, you need more fuel. But fuel has mass, and mass needs fuel to move it, which adds more mass, which needs more fuel, which adds more mass. It is an exponential spiral that collapses under its own logic before you ever get close to the speeds needed for interstellar travel. To push even a modest spacecraft to just 1/10 of the speed of light using conventional chemical rockets, you would need a quantity of fuel greater than the mass of everything on Earth, combined. You cannot engineer your way around this. You cannot throw money at it. You cannot wait for better materials. The equation is the equation. It is not an obstacle. It is a boundary condition of reality. So scientists started dreaming bigger, wilder. Nuclear thermal propulsion, ion drives that fire charged particles continuously for years. Even nuclear pulse propulsion, a concept from the 1960s where a spacecraft would ride the shockwaves of nuclear bombs detonating behind it. These ideas are genuinely extraordinary. Some of them might work. At their very best, they get you to maybe 5 or 10% of the speed of light, which means the trip to Proxima Centauri would take between 40 and 90 years. Better than 70,000, still an entire human lifetime, minimum. And none of these systems currently exist in any form capable of carrying people. They're blueprints, concepts, mathematics on a whiteboard. But even if you solved propulsion entirely, even if some future civilization cracked it, you would immediately crash into the hardest wall in all of physics: Einstein's special theory of relativity. Nothing with mass can travel at the speed of light. Not almost reach it, not get close and coast. As an object with mass accelerates toward light speed, the energy required to push it faster doesn't just grow, it approaches infinity. You could drain the entire output of the sun, and it would not be enough to push 1 single kilogram of matter to light speed. The speed of light is not a technical ceiling we might break through one day. It is embedded in the structure of space-time itself. It is the universe saying, this far and no further. And here's the thing nobody tells you. Even if you somehow solved propulsion and the speed limit both, the journey itself would kill everyone on board, long before they arrived. Outside Earth's magnetic field, space is a radiation environment so hostile that astronauts on the International Space Station, only 400 kilometers up, still partially shielded, receive 50 times the annual radiation dose of someone standing on the ground. In true interstellar space, with no planet's magnetic field anywhere nearby, cosmic rays would bombard the ship continuously, high-energy particles from supernova explosions slamming through the hull at nearly light speed themselves. And the cruel irony? If you build thicker shielding to block them, the particles hitting that dense material create secondary radiation inside the ship. You try to block the bullet, and the shield creates shrapnel. Then there's what happens to the human body without gravity. Bones lose 1 to 2% of their density every month. Muscles waste away. The heart shrinks because it doesn't need to pump against gravity anymore. Eyes change shape from fluid pressure shifts, causing vision damage that may never fully reverse. Astronauts spending 6 months on the ISS, exercising 2 hours every day, still come back measurably weaker. Multiply that for 40 years, or 80, or 200. The skeleton would be so fragile that the moment survivors stepped onto another planet's surface, the gravity alone could shatter them. And the psychological dimension is perhaps the most unsettling of all. At no speed below light, a radio signal from Proxima Centauri takes 4.24 years to arrive. A conversation with Earth, question and answer, takes over 8 years. There are no calls home, no news, no advice, no connection to anything outside the walls of a metal tube drifting through absolute silence for decades. Studies of isolated crews on Earth, people sealed in simulated spacecraft for months, consistently show psychological deterioration, depression, paranoia, conflict, cognitive decline. And those people could leave. They knew there was a door. On a real interstellar mission, there is no door. And if you extend the timeline long enough to need multiple generations to complete the journey, people born on the ship who never chose this, who live and die between stars, whose children and grandchildren are expected to maintain a mission they inherited, human history gives us almost no reason to believe that holds together. Languages change beyond recognition in a few hundred years. Cultures fracture. Institutions collapse. The idea of a sealed society staying unified and purpose-driven for centuries contradicts nearly everything we've ever observed about ourselves. We are almost there now. almost at the moment I promised you at the very beginning, the thing that reframes everything. Stay with me. Remember the ship, year 2247, the captain at the window. Here was the part I didn't tell you. That ship isn't failing because of a mechanical problem. It isn't failing because the mission was planned poorly, or the crew wasn't selected carefully, or the technology wasn't advanced enough. It is failing because of something far more fundamental. It is failing because the universe was not built with us in mind. The gap between stars is not an accident of geography. It's not a puzzle waiting to be solved. It is the natural state of a cosmos where matter organizes into islands separated by incomprehensible emptiness, and where the only thing that reliably crosses those voids is light, massless, bound by no rocket equation, slowed by nothing. We are not made of light. We are made of carbon and calcium and water and memory. We are biological creatures with a lifespan measured in decades, built for one specific planet, shaped by millions of years of evolution for a world with a particular gravity, a particular magnetic field, a particular sky. And here's the thing. Here's the peace that lives in the space between despair and wonder. We can understand it all anyway. The James Webb Space Telescope is right now analyzing the light filtering through the atmospheres of planets orbiting other stars, looking for the chemical signatures of life. We can read the composition of a world we will never stand on. We can detect the presence of oxygen, water vapor, methane from trillions of kilometers away. We can map alien weather systems. We can calculate the temperature of a planet's surface from here. Our intellect reaches further than our bodies ever will. And maybe that's not a tragedy. Maybe that's the most extraordinary thing about being human, that a creature who lives 80 years on a rock in one corner of the galaxy can sit down and understand the universe. The nearest star will never feel our footsteps, but it has felt our gaze for thousands of years. And now, for the first time in the history of life on Earth, something is gazing back with enough precision to ask real questions. We stood at the edge of the canyon. We measured it. We understood it. We built machines that can see across it. That's not nothing. That's almost everything. If this left you thinking differently about the night sky, subscribe. There's more where this came from. And tell me in the comments, where in the world are you watching from? The fact that we're all on the same tiny marble having this conversation is honestly remarkable enough on its own.